In this video, we will be discussing cell and half-cell potentials and how you calculate each. The difference in potential energy between the anode and the cathode in a voltaic, also known as galvanic, cell is called the cell potential. This same value in an electrolytic cell is the amount of energy or the amount of potential energy that you must overcome to get the reaction to be a spontaneous process. So the cell potential can either be the amount of energy that you can get out of a chemical reaction, in the case of like a battery, the energy in terms of voltage, or the minimum voltage that you need to supply to like an electrolytic cell to get the reaction to start becoming spontaneous. The cell potential itself depends on the relative ease with which the oxidizing agent is reduced at the cathode and the reducing agent is oxidized at the anode. The cell potential under standard conditions is called the standard EMF, or electromotive force, and will be represented with a variable E cell. Again, a superscript naught is used to denote that we're working under standard conditions. The standard conditions for an electrochemical cell are the same as the standard conditions that we were using when we were talking about enthalpy and Gibbs free energy, that being 25 degrees Celsius, 1 bar of pressure for gas, 1 mole per liter for concentrations of solutions. To figure out the standard electromotive force for an entire setup, we will be summing the cell potentials for the individual half reactions. Now, just like when we were talking about the Gibbs free energy and the enthalpies of formation, the electromotive force also has a standard reference value. In the case of the Gibbs free energy and the enthalpies of formation, or the Gibbs free energy of formation and the enthalpy of formation, the values listed in tables are relative to the elements in their most stable elemental form and the chemical that you're interested in, so the difference in energy. For reduction potentials, because we're looking at the driving force for a reaction, we need to compare it to another reaction. The reaction that gets used for standard reduction potentials is the standard hydrogen electrode, often represented with SHE. The standard hydrogen electrode is one in which you have an acidic solution down in the bottom, typically a platinum electrode. The platinum itself doesn't participate in the reaction. You have hydrogen, H2, at 1 bar of pressure being pushed in or extracted out, depending on whether it is at the anode or the cathode. And the force here is the electromotive force coming out of the standard hydrogen electrode is set to be 0. So we can't actually measure the absolute tendency of a half reaction. We can only measure it relative to other half reactions. So the reference half reaction is this standard hydrogen electrode. We select as the standard reference electrode the reduction of H plus to H2 under standard conditions, and we set the value for that potential difference to be 0 volts. Again, we will be calling this the standard hydrogen electrode. When we are using electrochemical cells to either do useful work or to do some sort of electroplating, we divide up the two components of the redox reaction. We separate the oxidation from the reduction in two separate cells. Each one of those cells is called a half cell. So we can swap out the different half cells in an overall electrochemical setup to get the desired voltage that we're interested in. So the standard hydrogen electrode reduction potential is going to be defined as being exactly 0 volts. We can then compare the tendency for a particular reaction to undergo reduction compared to the standard hydrogen electrode. So the standard reduction potential that you will find in a table is comparing the tendency for a particular reaction, for a particular reduction half reaction to occur relative to the reduction potential for the standard hydrogen electrode for the reaction of H plus going to H2 under the same standard conditions. So half reactions that have a stronger tendency towards reduction than the standard hydrogen electrode will be given a positive value for their E0 reduction that you will find in a table. The half reactions that have a stronger tendency towards oxidation than the standard hydrogen electrode will be given a negative value for the reduction. The values in the tables are going to be written in the reduction direction. If we're interested in using a particular half reaction for oxidation, what you would end up doing is flip the reaction, and so the driving force would then be going in the opposite direction. So what that means is, in terms of our half cell potential, if you have a particular value for the reduction and that has a particular driving force for it, then flipping the reaction around would flip the driving force. So the electromotive force for the oxidation half reaction is going to be opposite in sign to that same reaction if it was being used for reduction. So the E cell value for a reduction reaction is going to be the negative of the same reaction if it's being used for oxidation. Essentially, if we flip the reaction, we flip the sign of our half cell potential. Here is an example of a table of standard reduction potentials. You'll note that in each one of these are written in the reduction form. So you have your oxidizing agent picking up an electron being reduced into the reduced form. So here you have fluorine as a gas picking up 2 electrons going to 2F minus, and it has an E cell potential for that half reaction of 2.87. So the half reaction cell potentials are listed always in terms of their reduction potential. If you need to use the reaction in the oxidation form, you will flip the reaction and then flip the sign. Unlike our enthalpies and our Gibbs free energy, if you double the reaction, so for example, if we needed 2 nickels to balance out our reaction, here for the standard reduction potentials, you do not double the reduction potential. The total potential is going to be the sum of the 2 cell potentials once one of them has been switched for oxidation. The way that we will be calculating the cell potential under standard conditions for an entire electrochemical setup is by adding the cell potential for the oxidation half reaction plus the cell potential for the reduction half reaction. When we are adding the values for the 2 half reactions, we will not be multiplying the half cell values by any value, even if we need to double the reaction to get the number of electrons to add up to cancel out. We do not multiply the cell potentials. We just add them as is, straight from the table. The accounting for the number of electrons is done elsewhere in equations. So when we're adding up the total cell potential, we do not multiply by any factors. We just grab the values out of the tables. Whether or not we need 2 or 3 times the reaction, doesn't matter. Just add up the cell potentials. When you flip the direction of a reaction, you flip the sign on the electrochemical potential for the half reaction. So let's say we have chlorine going to chloride. It has a cell potential of 1.36 volts. If, on the other hand, we are doing the reverse reaction, and instead of having the chlorine being reduced, we have the chloride ion being oxidized to form chlorine, we flip the reaction, and so the driving force for the reaction is going in the opposite direction, which means that the cell potential becomes the negative of what it was before. So we flip the reaction, we flip the sign. The value is exactly the same as what it was before, but now we have this negative in front of it. So if you're using the value in the reduction direction, you will use the value straight out of the table. But if you're using that chemical reaction, the half reaction, in the form of oxidation, you end up flipping the reaction, and so you flip the sign. Let's now look at a couple of examples of how we would determine our overall cell potentials for some of the redox reactions that we used earlier when we were trying to balance redox reactions and determine oxidation and reduction half reactions. So our first example, we have Cl2 reacting with I- and H2O to form Cl- and IO3-. Now the values that are listed below each one of our reactions come from a table of reduction potentials for the half reactions. Whether we're looking at the oxidation or the reduction reactions, they have been currently listed out in the reduction direction. In each case, the electrons are on the reactant side, so in each case we are picking up electrons. So we are gaining electrons, so these are currently written in the reduction direction. So in order to add the two reactions together to get our overall reaction, in the case of our first set of half reactions, we would need to take our second reaction here and flip the reaction to convert it from being a reduction to being an oxidation. So that would give us I- plus 6OH- goes to give IO3- plus H2O plus 6 electrons. Now when we're trying to add these two reactions together, we need to make sure that the electrons cancel out. So I'm going to take the top reaction and multiply it by 3. Note when I'm doing this, I am not multiplying my cell potential by 3. So I'm multiplying this by 3, this would be 3 here, this would change to 6, and this would change to 6. When I took my oxidation reaction and flipped it, in order to do that, if you flip the reaction, you flip the sign, but you use the exact same value. So the cell potential for the oxidation would be negative 0.26 volts. I can now add my two reactions together, getting my overall reaction and figuring out the total cell potential. So that would be 3Cl2 as a gas plus 6 electrons plus I- plus 6OH- goes to give 6Cl- plus IO3 plus H2O plus 6 electrons. Our 6 electrons cancel out, and we get the same reaction as if we had done this particular reaction, balancing out the half reactions under basic conditions. Now to find the total cell potential for this reaction, we would add our two cell potentials together. So we're going to add this value with this value. So our total E cell would be equal to 1.36 volts plus the negative of 0.26 volts, which would give us 1.10 volts. So that would be the cell potential for this particular redox reaction under standard conditions. We can do the same thing for our next reaction. We would need to take our redox reaction, flip it, and so we would get H2C2O4 goes to give 2CO2 plus 2H plus 2 electrons. To get these two reactions to add together, I'm going to take the top one times 2 and the bottom one times 5. When I do the bottom one, I flip the reaction, so I flip the sign, so this would go from negative to plus 0.49 volts. So adding my reaction together, I would have 2 MnO O4 minus plus 16 H plus 10 electrons plus 5 H2C2O4 goes to give 2Mn2 plus 8 H2O plus 10 CO2 plus 10 H plus 10 E minus. My electrons cancel each other out. 10 of my H pluses here leave me with 6 H pluses on the left-hand side. I now have a balanced reaction. My total E cell is going to be the reduction half potential plus the oxidation half potential. So the E cell would be the sum of those two values, which would be 1.51 plus 0.49, which would be 2.00 volts. Note that although I took the top reaction, multiplied it by 2, and the bottom reaction and multiplied it by 5, I did not, when I was summing up the two values, multiply the voltage by 2, and I did not multiply this voltage by 5. You just use the values as they are. The scaling factor when we are talking about moving 10 electrons gets taken into account later in calculations. For now, the voltages, right, those are just the sum of the two cell potentials. In our last example, I need to flip my oxidation reaction. So I'm going to take my CrO42 minus, move it to the other side. So that would give me CrOH4 minus plus 4OH minus goes to give CrO42 minus plus 4H2O plus 3 electrons. Okay, so to get the electrons to cancel out, I need to take my top reaction and multiply this by 3. Again, I do not multiply my voltage by 3. For my oxidation reaction, because I flipped the sign, so this would become plus 0.12 volts for the reaction written here. So I need to take the top reaction, multiply it by 3. The bottom reaction stays as is because it already has 3 electrons. The electrons will then cancel each other out. So writing out the full reaction, this would be ClO minus 3 ClO minus plus 3E minus plus 3H2O plus CrOH4 minus plus 4OH minus plus 3Cl minus plus 6OH minus plus CrO42 minus plus 4H2O plus 3 electrons. Canceling the things that are the same on both sides. I got my 3 electrons here, 3 electrons there. These 3 water will cancel out all but one of those waters. And the 4 hydroxide here will cancel out all but 2 of the hydroxides there. And this here should be an arrow. Okay, so adding the two cell potentials together to get my overall cell potential, my E naught cell would be this value here plus this value here. So it would be 0.89 volts plus 0.12 volts, which would come out to be 1.01 volts. So those are our answers for the cell potential. Again, the key thing to keep in mind is that unlike when we were working with Hess's law, when you, in the case of enthalpy and Gibbs free energy, when you doubled a particular reaction, you doubled the value. For cell potentials, you don't do that. When you flip the reaction, you still flip the sign, but when you double the reaction or quadruple the reaction or take 5 times the reaction, you keep the cell potential to be the same value as you had it before. The cell potentials that we calculate will tell us whether a reaction is going to be spontaneous or not. A spontaneous reaction will take place when a reduction half reaction is paired with an oxidation half reaction that is lower on the table. This will give us a positive net cell potential. So in the values that we had previously calculated, those all gave us positive net cell potentials, and so those would all be spontaneous processes. If we pair the other way around, then the reverse reaction will be spontaneous, meaning that the direction that we are trying to do, as it is written, would be a non-spontaneous reaction. So it would have a negative cell potential. So if we look at copper, Cu2+ being reduced to form copper solid, it has a reduction potential of 0.34 volts. For zinc, going from zinc 2+ to zinc metal, it has a reduction potential of negative 0.76. So zinc is lower on the reduction table than copper. So if we pair copper as being a reduction or being reduced, and the zinc as being what's oxidized, in the case of we have the copper 2+ reacting with zinc solid, essentially we're taking our second reaction here, flipping the reaction. So instead of going from zinc 2+ to zinc solid, we're going from zinc solid to zinc 2+. This reaction will be spontaneous. So we are flipping the bottom reaction. If you flip the reaction, you flip the cell. Adding the two together, you'll get a positive value. However, if we do it in the reverse direction, i.e. taking our zinc 2+ and having that be the reduction reaction and the copper being the oxidation reaction, we would be taking the top reaction, flipping the reaction, going essentially from copper solid to copper 2+. Because we flip the top reaction, we flip the sign, and then we add the two together. And in that case, we would be taking negative 0.34 plus negative 0.76, giving us a negative value for the overall cell potential. And that would tell us that we would have a non-spontaneous reaction going in the reverse direction. So how can we use these cell potentials in a real-world type problem? Well, a lot of metals, when we're trying to get them to dissolve up into solution or purify them, a common method is to put them in an acidic solution. Some metals will react with any acid in general because they are reacting with the hydrogen ion, forming hydrogen gas, and it is the cell potential for that particular metal is lower in the table, in the reduction table, than the standard hydrogen electrode. If that's the case, then that metal will dissolve in any acid. However, some metals are non-reactive to just any acid. If we were to take copper, for example, and try to put it into maybe hydrochloric acid, you would find that the copper metal is non-reactive towards hydrochloric acid. However, nitric acid is an acid that will dissolve almost all metals. Not necessarily all, but most of them. Most metals will dissolve if placed in nitric acid. The reason for this is that it is the nitrogen that is being reduced rather than the hydrogen. So you could have NO3 ions, the nitrate ions, plus 4H plus 3 electrons going to NO, nitrogen monoxide gas, plus 2 waters. This particular half reaction has a cell potential of 0.96 volts, which is much higher than a lot of metals, which means that this reaction can be used in the reduction reaction in order to oxidize most metals, converting them from the metal form into their more oxidized cation form. And so if you want to get a metal to dissolve up into a solution, you can generally put it in nitric acid and it will dissolve.